Hi guys, in this tutorial we are going to talk about a novel evolutionary algorithm called Cuckoo optimization algorithm. This algorithm is one of the most effective and high performance algorithms in the category of evolutionary optimization algorithms. And in this tutorial we're going to see the codes, the core codes for this paper, which you can find it on Elsevier, and I highly propose you to read this paper once to understand what it is talking about and how it's working, and check if you want the results in this section 4. They test benchmark functions and whatever. We're going to talk about the codes for this algorithm. Maybe you ask why you're insisting of this one and why you selected this special one. I have to say that the higher convergence rate and faster results and also precision in the results is among the properties which this algorithm has. So we're going to see how the core codes for this algorithm works and how you should write your cost functions to get the best results from this algorithm. First of all, we have to copy the folder path to the current directory of MATLAB and then open Cuckoo main M file. Okay. From this many lines of codes here, you just need this part. Okay, this part consists of some parameters for your problem and some parameters to get the best results out of a Cuckoo optimization algorithm. Many people make a mistake in selecting the algorithm. I mean, there is another algorithm out there called Cuckoo search, or CS in abbreviation. Notice that these two algorithms are totally different and they're not the same, even if they have the same name of Cuckoo. Cuckoo search is just a local searcher. So if your problem is a global optimization, then you need to use this code and the Cuckoo optimization algorithm, or you will not get a good result and you may be waste your time with a local searcher. Here you see some parameters for your problem. For example, number of parameters to be optimized is written and entered in pair, and minimum or lower band and upper band of the search space is entered in two parameters called var low or var high for the upper band, and these are some other parameters which are special to Cuckoo optimization. For example, number of cuckoos, number of initial cuckoos, of course. Here it is set to 5. Number of eggs, for minimum number of eggs for each cuckoo is set to 2. Maximum number of eggs is currently set to 9. You can play with these parameters. And maximum iterations is currently set to 100. Number of clusters in which divide the cuckoo population over the search space is currently set to 5. Motion coefficient or immigration coefficient, which says how fast the cuckoos move towards current global best position, is entered as 4. And if you are working with a cost function that takes negative values, then you have to set accuracy to -infinite. Otherwise, if your cost function only takes positive values and its minimum is in ideal situation is 0, then you can easily set this to 0. Otherwise, I normally say let it be -infinite. Maximum number of cuckoos currently is set to 30 because in cuckoo optimization algorithm the population size is not a constant value and varies over time, so we have to limit its maximum size. Otherwise it will increase the population all over the search space, and this is not effective. It is not a effective search methodology. Radius coefficient or egg-laying radius, which controls in which radius cuckoos are going to lay eggs, is currently set to 3, and you can play with all these parameters, and a convergence rate, a stop criterion, is defined here. If all the variance of all population is less than this number, optimization will break and the final result will be shown, because it's consumed that it's supposed that the algorithm and the cuckoos are all gathered in a single position. Okay, to use this algorithm you have to write your own cost function. There is a template for the cost function you have to write, and we are going to see that template. Let's make a new M file, write the keyword function, provide a variable as output, give a function name, my cost function for example, and provide a name for population matrix of cuckoos. Then, because the population matrix in other evolutionary algorithms like genetic algorithm or particle swarm or whatever, they are fixed size, and this population matrix in those algorithms have same number of rows in each iteration. But here in this evolutionary algorithm in the COA, I mean population size, I mean number of cuckoos thrown from cuckoo main to cost function varies in each iteration. So we have to get number of rows or number of cuckoos at the first line of this cost function. So let's say number of cuckoos be size of cost matrix and 1 this way. Okay, now let's initialize our cost vector as zeros of size number of cuckoos and 1, it's a vertical vector of size number of cuckoos. Why are we initializing cost vector as in this form? It's because we get a population matrix and we want to evaluate each row of that matrix and then put the corresponding cost value in the corresponding position of this output value. Now, the most important part of this template I'm going to show you is a for loop with number of rows, number of cuckoos, and end. Okay, this is the loop. Let's save this one. This is the loop that goes over the rows of population matrix. So in the first line of this loop we have to get current row of our current cuckoo, if you want, let's say current cuckoo, okay, on row I and all columns. Okay, the final part of this template is cost in position I defines in whatever formula it has. Have in mind that you have to use such templates, always this template for Cuckoo optimization algorithm. We are going to fill in this part in a minute, but I want you to memorize this template and use only this style in your codes, because otherwise you will get errors and Cuckoo optimization algorithm or this Cuckoo main M file will not work and will throw different kind of errors. Let's say that we are going to have a cost function with 3 parameters, okay? Then we have to set number of parameters to 3, and this makes our population matrix to have 3 columns, or each cuckoo here, each current cuckoo will have 3 values. Let's get these 3 values out of it this way. 1, x2, element number 2, and x3 is the element number 3. Okay, now how do we use these parameters? It's on you, it's on your cost function formula. Let's say that we are going to minimize such a function. x1 minus 1, x2 minus 2 to the power of 2, and x3 minus 3 to the power of 2. Okay, this is a very simple cost function, which its minimum value is 0, and we know that if x1 is equal to 1 and x2 equals to 2 and x3 equals to 3, this cost function will be 0 and its minimum value will be obtained. So let's go back to the main code and run the program. I don't touch anything here, and or even search space, it's big enough to search, and we have 3 parameters. Oh, the only thing I need to copy here is the name of my cost function. Okay, let's save all of these and run the program. As you see, it's really fast and it finds best result. You see that up here in even 10 iterations or less. You see that ideal results are obtained here. X1 is almost 1, x2 is almost 2, and x3 is almost 3. And the cost function proves that the result is ideal because it's really negligible. Suppose that you're going to optimize a higher dimensional cost function. What can you do or to make this cost function more general? Let's comment this out and delete this part. I want to define the size of optimization, the dimension of optimization, by changing only this number. Okay, so we don't have only 3 columns, we have n columns. To do that, we can write simply, for the same problem, of course, we can simply write sum of something to the power of 2, sum of current cuckoos, okay, current cuckoo minus, we need an index. In the previous example I wrote x1 minus 1, x2 minus 2. I want this 1, 2, 3 index. To produce that in a row, we can simply write 1 to until number of elements of current cuckoo. Okay, this produces the indexes, and this is a vector of x1 until xn. Okay, now let's go back, let's save this first and go back to the main program and test this with even 3 parameters first to check if it's correct. That seems to be correct, and the cost function, oh, that's great. Okay, we see that the results are ideal and everything is okay. Now I want to increase this. For example, let's say 7 parameters. It automatically changes here to a function of x1 minus 1, x2 minus 2, x3 minus 3, to x7 minus 7 to the power of 2, and then the summation of this formulas are gathered in my cost function. Now let's run this one. Okay, as you see, again, the cost function value is really negligible, and the proof for that is the great results and ideal results seen here. You see that x1 is 1, x2 is 2, x3 is 3, x4 is 4, and 5, 6, and 7. Okay, so you can easily work with this with any number of parameters. And for example, if you increase this, let's say 15, then you get let's suppose we get a bad result. What can we do? We can play with these parameters. We can increase maximum number of cuckoos, we can increase number of iterations, we can increase or decrease motion or immigration coefficient, or coefficient which limits the egg-laying radius. You can play with these parameters if you get bad results. Let's run this code for 15 parameters and see what happens. If it's bad, we can play with parameters to get better results. Okay, now look at this cost value. It's 11.7. It means that some of these values here are not ideal. Okay, we can simply increase this to 200 and run the code again and see what happens. See, it's going to decrease to 1 and it moves towards 0. Okay, now let's do the results. Results are satisfying now, more satisfying in comparison with the previous run. The cost value is only 0.7 and these values for 15 parameters, optimization parameters, are really satisfying. Okay, the most important part of this tutorial is to see the templates, I mean this template for the cost function, for the suitable cost function of Cuckoo optimization algorithm. If you use this template, you won't get any errors. If you ignore this for loop, you will get errors, because Cuckoo main, or the main optimization algorithm, always supposes that when it provides you with a population matrix, you are going to give back and pass a cost vector of size number of cuckoos. Okay, so simply use this and only this template and write your cost function, or you can have some other codes here. Okay, let's say write your computations here. You can write any computations and lines here, and at the last line you can enter your final code. You may have hundreds of lines here between current Cuckoo and the final cost value. Okay, add them and simply enter your cost value to this final line, and then save the code and run the Cuckoo main. I'm going to the previous state of this cost function because maybe someone wants to test it for his training. So I don't change any part of this, and I let this, for example, 5 or 7 or whatever. You don't need to know what happens in the core code because it's really long, and I don't think anyone be interested in that code. The only thing you need to know is that this part of code highlighted here is the only part you are going to use. If you want to get these codes, they are in the file exchange section of MathWorks website. You can get it there, or you can simply email me through these 2 emails here. Okay, you can email me or go to the MathWorks website and the file exchange. You can get the codes. Of course, I propose you to get the most recent codes, because I have done some improvements in this code I'm using here in this tutorial, which are not in that version of MathWorks, but both are correct. This one is just a simple, little more improved version. Have a good day, guys, and I'll be waiting you to use this algorithm with success. And in the next tutorial, I may go to the basis of this algorithm and to see what happens in this paper, And if you are interested in the results and to see what's the core and the basis of this algorithm and how it works, you can watch the next tutorial. I'll be providing you with, and I can say goodbye until that moment.